The universe contains an estimated 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. And among all of those stars, some are so impossibly large that our entire concept of big completely breaks down. Today we are going to rank the stars from the smallest to the most enormous object the universe has ever produced. And every single number you are about to hear is real. Let's start with something familiar. Earth has a diameter of about 12,700 kilometers. That's our baseline. Everything from here gets bigger. Much bigger. Jupiter, the largest planet in our solar system, has a diameter of roughly 143,000 kilometers, about 11 times wider than Earth. It is so large that all other planets in the solar system could fit inside it simultaneously. And yet Jupiter is not even close to being a star. It has the right ingredients, mostly hydrogen and helium, but only about 1/1000th of the mass needed to ignite nuclear fusion. It's a giant that never quite made it. Between planets and stars sits a strange category called brown dwarfs. These objects range from about 13 to 80 times the mass of Jupiter. They are massive enough to trigger some low-level nuclear reactions in their cores, but not powerful enough to sustain full hydrogen fusion like a real star. Their core temperatures reach around 2000 to 3000 degrees Celsius hot, but nowhere near enough. They glow dimly in infrared light and slowly cool over billions of years. Not a planet. Not a star. Scientifically awkward. To become a genuine star, an object needs to reach a core temperature of at least 10 million degrees Celsius. At that point, hydrogen nuclei are forced close enough together to fuse into helium, releasing enormous energy. That energy pushes outward, gravity pulls inward, and the star reaches a stable balance. This is called the main sequence, the longest and most stable phase of a star's life. The smallest main sequence stars are red dwarfs. A typical red dwarf has a diameter of roughly 200,000 to 300,000 kilometers, about 15 to 20% the size of our Sun. Their surface temperatures sit between 2,500 and 4,000 degrees Celsius, which is why they glow red rather than yellow or white. Because they burn fuel so slowly and efficiently, red dwarfs can live for 10 trillion years. For context, the current age of the universe is only 13.8 billion years. No red dwarf in existence has died yet. They make up approximately 70% of all stars in the Milky Way alone. Our Sun sits comfortably above that range. It has a diameter of 1.39 million kilometers, about 109 times wider than Earth. Its surface temperature is around 5,500 degrees Celsius, and its core reaches 15 million degrees Celsius. It produces 3.8 times 10 to the power of 26 watts of energy every single second, a number so large it is essentially meaningless to say out loud. The Sun contains 99.86% of all the mass in the entire solar system. Every planet, moon, asteroid, and comet combined makes up only the remaining 0.14%. Moving up, Sirius A, the brightest star visible from Earth, has a diameter about 1.7 times that of the Sun, a surface temperature of nearly 10,000 degrees Celsius, and shines with 25 times the Sun's luminosity. It is only 8.6 light-years away, making it one of our closest stellar neighbors. Despite being just under twice the Sun's mass, it is already dramatically brighter because brightness scales very steeply with mass in main sequence stars. Continuing upward, blue giant stars with around 10 times the Sun's mass reach surface temperatures of 20,000 to 30,000 degrees Celsius. Beta Centauri, a well-known example, shines with approximately 20,000 times the luminosity of our Sun. These stars live fast and die young. Their entire lifespan from birth to death lasts only 10 to 20 million years, compared to the Sun's 10 billion year lifespan. Now here is where things get counterintuitive. The most massive star ever recorded is R136A1, located about 160,000 light-years away in the Large Magellanic Cloud. It carries over 300 times the mass of our Sun and radiates approximately 9 million times more energy. You would expect a star with 300 solar masses to be absolutely enormous in physical size. But its diameter is only about 30 to 35 times that of the Sun. Massive but not physically huge. Why? Because stars of extreme mass burn so violently that their intense radiation constantly blasts material away from the surface. R136A1 loses mass equivalent to the Earth's mass every single month through its stellar winds. It is too energetic to hold itself together properly, and certainly too energetic to expand outward. Extreme mass does not equal extreme size. So how do stars get physically enormous? They have to start dying. When a massive star exhausts the hydrogen fuel in its core, the core contracts rapidly under gravity and heats up. This triggers faster and more intense fusion reactions in the surrounding layers. That additional energy output forces the star's outer envelope to expand dramatically, sometimes to hundreds of times its original diameter. The star has entered its giant or supergiant phase. Our own Sun will one day expand to roughly 200 times its current diameter, engulfing Mercury, Venus, and possibly Earth in the process. That sounds catastrophic, and for Earth it will be, but on the scale of the true giants, our expanded Sun will still be relatively modest. The largest class of stars physically are called red hypergiants. These are the bloated, dying final phases of the universe's most massive stars. Their surface temperatures drop to around 3,500 degrees Celsius, cool enough to appear deep red, but their sheer surface area means they still radiate hundreds of thousands of times more energy than our Sun. Rho Cassiopeiae is one of the most studied yellow hypergiants and gives a sense of this scale. It spans roughly 500 times the diameter of the Sun and shines with around 500,000 times its luminosity. It sits thousands of light-years away, yet remains visible to the naked eye on a clear night, a testament to just how much energy it is pumping out. But the current record holder for physical size is Stevenson 2-18, a red hypergiant located about 20,000 light-years from Earth inside a massive star cluster. Current measurements place its diameter at approximately 2,150 times that of the Sun. In actual distance, that translates to a diameter of roughly 3 billion kilometers. Let those numbers do the work. The Sun's diameter is 1.39 million kilometers. Stevenson 2-18's diameter is approximately 3 billion kilometers. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Saturn, the sixth planet out. Jupiter, the gas giant we started with, would be orbiting deep inside the star. Traveling around its equator at the speed of light 300,000 kilometers per second would take approximately 8.7 hours. On a commercial aircraft it would take roughly 500 years to complete one lap. Stevenson 2-18 is so large that gravity at its surface is extremely weak. It is slowly losing mass into space through powerful stellar winds, shedding its outer layers continuously. Eventually its core will accumulate enough heavy elements, iron, nickel, that fusion stops entirely. The core will collapse in a fraction of a second, and the resulting explosion, a core collapse supernova, will briefly outshine entire galaxies. The material ejected will drift through space for millions of years, eventually being swept up into new collapsing clouds, forming new stars, new planets, and beginning the entire cycle again. Every element heavier than hydrogen and helium, carbon, oxygen, iron, the calcium in your bones, the iron in your blood, was forged inside a star and scattered by exactly this kind of explosion. You are, in the most literal and scientific sense, made of dead stars. And somewhere out there, a star 2,150 times wider than our Sun is slowly preparing to add its own material to that ancient cycle.